All right, so those are just your endpoints. To see which maximizes revenue. Okay, so we know that R of 100, that's a little bit messy there. Okay, so R of 100 is equal to, where is it? I'll use this one so we don't have to worry about squaring anything. So 800 minus 4 times 100 times 100. Okay, so that's equal to 800 minus 400 times 100 is 40,000. Okay, so now we do the same thing, kind of separate that a little bit, for R45. So if you charge $45 per rental, that would be 800 minus 4 times 45, and that all times 45. Plug that into your calculator and you get 27,900. Now if we charge $200, our 200 is equal to 800 minus 4 times 200 times 200. Uh-oh. Uh-oh. Okay, so you have 800 minus 800 is 0, so if you charge 200 bucks, you actually just break even. So you make the most money when you charge $100 per rental. So $100 maximizes revenue. Bring that up a little bit. All right, so any questions on that one? All right, I'll leave that up there for a little bit.
When it goes through the domains, if you're looking for the maximum, will the n, or the larger of the domain, always be 0? And then the minimum, the smallest number would always be 0?
Not always.
That's just how it works.
Yeah, just so happens on this one. Sometimes it's possible, depending on what the equation for the number of cars, it's possible that the 200 would have given you the maximum revenue. So all depends on how it's kind of thrown in there. All right. So hopefully this step process makes it a little bit easier. Okay, so now we're going to start on L'Hopital's rule. Uh-oh. Make that a little bit messy. And this is just one of those finding a limit shortcuts. So if we let some function x and some function g represent differentiable functions, where we know that the first derivative of g doesn't equal 0. So they both have a derivative. We just know that the g of x won't equal 0. G prime of x, rather. All right, so if the limit of f of x over g of x as x approaches some number c equals 0 over 0 if you use direct substitution, where this is called an indeterminate form. And a little quick side note, let's say infinity over infinity, negative infinity over infinity, infinity over negative infinity, or even negative infinity over negative infinity are also indeterminate forms. So this would work if you had any of these or 0 over 0. Okay, so if it equals that through direct substitution, kind of separate that a little bit. Then we know that the limit of f of x over g of x as x approaches c is equal to the limit of the derivative of both of those as x approaches c. All right, so let's say, for example, what if you want to find the limit of 2x squared minus 2 over x plus 1 as x approaches negative 1? Okay, so if we use direct substitution, then that would give us the limit as x approaches negative 1 of 2x squared minus 2 over x plus 1. If you plug in negative 1 in your denominator, you get 0. Plug in negative 1 here, you get 2 minus 2, which is 0. So we have our indeterminate form, which means we can use L'Hopital's rule. So we just have the limit as x approaches negative 1 of the derivative of 2x squared minus 2 over the derivative of x plus 1. Okay, which gives us the limit as x approaches negative 1. Bring down our 2 here. We have 4x. Derivative of x plus 1 is just 1. So now we try direct substitution again. 4 times negative 1 over 1, which is just negative 4. So we know that the limit of 2x squared minus 2 over x plus 1 as x approaches negative 1 is equal to negative 4. All right, so any questions on that one? All right. All right. Actually, these just make things a lot easier.
But you gotta write the limit of x as the x approaches the negative one. You gotta write it every time. Like my old calculus teacher, he used to make us write it every time.
I was told if you write it more than once, you're taking the limit when you already took the limit.
Yep, so you can do it multiple times.
Like for every step, you gotta write it.
All right, so let's say, for example, I want to find the limit as 3x squared minus 1 over 2x squared plus 1 as x approaches infinity. Let me make that 2 a little bit clearer. All right, so if we have the limit 3x squared minus 1 over 2x squared plus 1 as x approaches infinity, we know that if we plug in a really big number that's getting bigger and bigger and bigger and bigger and bigger, your numerator is just going to keep getting bigger and bigger and bigger and bigger and bigger. So your numerator is going to approach infinity. Same thing with your denominator. If x just keeps getting bigger and bigger and bigger, your denominator is just going to keep getting bigger and bigger and bigger. Okay, so we have your indeterminate form. Okay, so that means we can use L'Hopital's rule. Okay, so that means you have the limit as x approaches infinity of the derivative of 3x squared minus 1 over the derivative of 2x squared plus 1. Okay, which will equal the limit as x approaches infinity. Bring down our 2 here. We have 6x over, bring down our 2. Well, that just becomes 0, derivative of 1. Bring down our 2 here, so we're 4x. Okay. So you can just go ahead and cancel out the x's if you want to, or you could apply L'Hopital's rule again. And you just end up the limit as x approaches infinity of 6 over 4. Okay. So we know that if it's constant, it doesn't matter what you're approaching. It's just going to be a constant. So that's 6 over 4, which simplifies to 3 over 2. All right. So any questions on that one? All right. So let's say if we have the example, we have the limit of e to the x minus 1, bless you, over x squared as x approaches 0. Okay, so the limit of e to the power of x minus 1 for x squared as x approaches 0. If we plug in 0 for our denominator, we just get 0 squared, which is 0. If we plug in 0 on our numerator, anything to the power of 0 is just 1. So you have 1 minus 0 minus 1, which is 0. Which means we have an indeterminate form, so we can use L'Hopital's rule. Okay, so that means we would have the limit as x approaches 0 of the derivative of e to the x minus 1 over the derivative of x squared. Okay. Which would give us the limit as x approaches 0. The derivative of e to the x, remember that's just e to the x. Derivative of x, that would just be minus 1. Over derivative of x squared, which is 2x. Okay. So if we plug in 0 again, anything to the power of 0 is just 1. So you have 1 minus 1 equals 0. Plug in 0 here. 2 times 0 is 0. So again, we have an indeterminate form. So we use L'Hopital's rule again. So now we end up with the limit of the derivative of e to the x minus 1 over the derivative of 2x as x approaches 0. Oh, bring that up some. Okay, so that gives us the limit. Derivative of e to the x is again e to the x. Derivative of 1 is 0, so that disappears. Derivative of 2x is just 2. So now we plug in our 0 again. So that's e to the 0 over 2, which is 1/2. All right, so any questions on that one? All right. Oh, he wants to write it. Okay, now probably the most important thing to remember the limit must equal a determinate form before you can use L'Hopital's rule. Indeterminate, I don't know why I said determinate. Okay, which means that if it doesn't, you can't use it. So remember, that's just your 0 over 0, or any combination of positive and negative infinity over infinity. Now, if you have it in the form, let's say 0 times infinity, infinity times infinity, 0 to the power of 0, or infinity minus infinity, will have to be converted. Before using, L'Hopital's rule. Well, might as well say limits that equal. There we go. Yes.
Quick question. So
Mhm.
for the indeterminate forms, would it matter if, could you be infinity over negative infinity?
Oh no, any combination would work.
So that would still be indeterminate?
Yeah, it would be. Yes.
What about 1 over 0 or 0 over 1?
Those would be undefined. Now the limit as it approaches 0 can be 0, but it just can't actually equal 0. Unless you have 0 over 0, then you can apply L'Hopital's rule.
So what do you mean by these ones would have to be converted?
If you plug in your direct substitution and you end up with any one of these, you'd have to kind of manipulate the function to make it equal infinity over infinity or 0 over 0. Okay, so let's say, for example, if we have the limit of e to the negative x, square root of x, as x approaches infinity. Okay, so e to the negative x, that's just 1 over e to the x. Okay, so if we have the limit of 1 over e to the x as x approaches infinity times square root of x. Okay, so if you have 1 over e to the x, let's say you just have 1 and e to the x, as you get bigger and bigger and bigger, your denominator gets bigger and bigger and bigger. Which means that a constant divided by a number that's getting bigger and bigger and bigger just gets closer and closer and closer to 0. So this just becomes 0 times square root of x. If you have square root of a really big number, that's still just a really big number. So as the number gets bigger, the square root just keeps getting bigger. So you have 1 times infinity. 0 times infinity. Why do I keep saying 1? Which is not indeterminate. Which means we can't use L'Hopital's rule. Okay. So now we just have to manipulate it a little bit. So instead of 1 over e to the x times square root of x, we make it, and sometimes it's just a little change, square root of x over e to the x. That little change make all the difference in the world. Because as x gets bigger and bigger and bigger, your numerator gets bigger and bigger and bigger. And here, as x gets bigger and bigger and bigger, this doesn't go towards 0. This just keeps getting bigger and bigger and bigger. Okay, which is an indeterminate form, so now we can use L'Hopital's rule. Okay, so that means we have the limit of the derivative. Instead of square root of x, I'll write it as x to the 1/2 power over the derivative of e to the x as x approaches infinity. Okay, so the derivative of 1/2, x to the 1/2 power, bring down our 1/2, and we subtract 1. Which 1/2 minus 2 over 2 would make it negative 1 over 2, or negative 1/2. Divided by the derivative of e to the x is just e to the x as x approaches infinity. All right, so since that's negative, we can just bring our square root of x down here. Since this is 1/2, we can just bring the 2 down here. So you have the limit of 1 over 2 square root of x times e to the x as x approaches infinity. Okay. So really you just plug in really big numbers, that denominator just keeps going and going and going, keeps getting bigger and bigger and bigger. So you get 1 over the limit of all of that as x approaches infinity, which is equal to 0.
So the limit would be out front. It wouldn't be limit of x as a.
Well, actually, you can get the limit of both. So the limit of 1 over the limit just from the
Well, I'm
properties.
saying, like, if you wrote it that way, would
Mhm.
that be correct or no? Or would you have to write it the other way? 1 over the limit of x approaches infinity.
Oh, I just wrote this here just because you couldn't put 0. So just kind of justify that you can't put 1 over 0. But in this case, this is just the limit is equaling to 0.
Okay, that's fine.
Okay, so since you have a limit that's equaling to 0, if you divide 1 by, if you think of it this way, 0.1, that would be 10. If you divide it by 0.01, that would be 100. Then if you 0.000 and exactly that, then it just keeps getting bigger and bigger and bigger.
Okay.
So the smaller this one gets, it just gets closer and closer to, closer and closer to 0. I don't know why I was about to write 50. Oh, infinity, that's right. Duh. Kind of moving around here. There we go. Mixing my steps up. All right, so we know that the limit of e to the negative x, square root of x, as x approaches infinity, is equal to 0. All right, any questions on that one? Okay, so let's say if we have the example. To find the limit of 2 divided by tangent of x minus 7 over x squared as x approaches 0 from the right. And that's getting ready to shut off.